few functions. One policy, right? Policy frames. We've got policy update, which is policy update by doing stochastic gradient descent on this gradient. Gradient with respect to the policy parameters is 1 over the size of B, sum over all of the states in the batch. And then I given 1 to 2, Q, theta, I, S, A tilde, theta, S, minus, and then you have your entropy term, which is alpha log I theta, A tilde, theta S, given S. Okay. And this guy, A tilde theta S, is a sample from pi theta S, which is differentiable with respect to pi, the reparametrization. But that's all that's relevant for this stuff. What's going on? Okay, so just one policy network. Where do they describe the design? Corresponding algorithm converges to the optimal policy from its density class, then present a practical, deep reinforcement learning algorithm based on its policy theory. So the policy, the value functions are modeled as expressive neural networks. So taking that to mean they just output the numbers. And then the policy is the Gaussian with mean and covariance given by neural networks. see. So it should be vector valued because you should have a bunch of different outputs that you can have. So that's why they're talking about covariance, because it's not just going to be one number. So covariance of something with itself is going to be just the variance of that. So you'll get a big matrix of covariances instead of just one variance per output. You'll just output this big, like if you have two outputs, you'll output like a planar Gaussian. It's kind of for each of the axes, you'll have covariance for these two and that and all on. So 4 numbers for your variances and 2 means. So n squared covariances, n means. So how they sample this. The state value function approximates the soft value. There is no need in principle to include a separate function approximator for the state value since it's related to the Q function in policy according to equation 3. This is all not interesting. I don't care about the Q functions because they're straightforward. The target weights are all for the Q functions. We reparameterize the policy using a neural network transformation. So AT the action at time t, the sample, no, it's equal to f theta should be phi. But are they using the same thing throughout? So our theta is their phi.
I haven't seen the KL divergence of theta before.
You hadn't?
Well, like not for this algorithm.
What are you referring to, like this part?
Yeah.
Yeah, it's just saying you're going to measure the distance between. So this is policy at the current state. So that's the output probabilities. And then this is this reads weird because x is like exponential. That's not an expectation.
Is this not like the next action taken?
So that means like what you can do is you say that is,
Because usually I've seen it just defined as like the entire like spread of probabilities across your output vector, but like our output vector isn't that.
it will be because so you're outputting a couple things. So they've got, let's see, what should this be actually? This is going to output means and covariances.
Yes, yeah.
So you get a probability distribution over. So you have a continuous action space. So like if you have 2 base actions, you actually pick a combination of them. So the action you pick is some point in this space. And this is just a probability distribution over the linear combinations of action bases. Basis actions. So you can, that's a probability distribution, so you can take and pull that Linear divergence of that against something else. But what is that thing on the right hand side? X. Q. Thrusts. V. S. T. And then any action. Over. Z. And I think this is the target. No, that's not. That should be like a return value function.
You're saying Z is the target, or?
I feel like it is the. I feel like this should be this. Like this is a softmax or something. So this should be like a sum over all the actions, maybe. Something to that effect. They probably used it earlier. Here. Partition function normalizes the distribution. While it's intractable in general, it doesn't contribute to the gradient. With respect to the new policy, it must be ignored. So it says partition function. It doesn't come up in the calculations, but it doesn't come up in the computation algorithm at all. It's a really poorly written paper, actually. A lot of typos and not being clear. No, we can do. No, the computer works. So first I want to see the inference. Where's that being done? Actor policy, so SAC policy should be probably in here. Forward. This is tough to read, actually. they got a bunch of stuff in here that's like optimizations for exploration. Like they've got state dependent exploration. So you probably store some vector states or something and then change whether you are likely to explore based on those.
Yeah.
You got perturbations to your policy distribution. So let's see. Get standard deviation. So what is action dist? Action dist. State-dependent noise distribution. Otherwise, it's a squashed diagonal Gaussian distribution. So that is defined here. So here's a reparametrization trick. So actions are sampled? What? That's an abstract method. Oh, I see. Check me on this.
Yep.
So in this probability distribution, squash diag Gaussian distribution, there is a function called sample. So presumably you're calling this when you want to get a sample from that distribution, which should probably be like that point in the spherical Gaussian.
Yeah. How do you define that though?
So they say, okay, self.Gaussian actions equals super.sample, and they actually perform sample. Now, what is super? Well, super is this distribution. And what's funny is it's an abstract method that isn't implemented. So what that means is the inheriting subclass, this, I might be wrong. Go took me to the wrong place. So this has to actually implement the sample function. So it's actually, if there weren't this in the way, and I had just put distribution here, then this would be calling itself and storing the result in Gaussian actions. But then it would call itself and store that, and it recurses forever. So completely just nonsense. So actually, this is what I was missing. So sample should be in here. Okay. Reparametrization trick. Distributions should have our sample.
Yeah, I think our sample is just, I forgot which library it comes from.
It should be in distributions. So this inherits from ABC. What was that? From ABC, import ABC. Okay, abstract base class. And distribution is defined to be none here. So in this, it should be
There you go.
it's normal.
Where's the actions?
So torch.distributions. Okay. So the reparametrization trick is just in PyTorch. So the other way to implement these stochastic or policy gradients would be to use the reparameter trick in the rsample method, where the parameterized random variable can be constructed via a parameterized deterministic function of a parameter-free random variable. Parameterized random variable we constructed via a parameterized deterministic function of a parameter-free random variable. That's true. So what they're doing is they're saying the parameters are the parameters for the policy network. M is the normal distribution with those parameters. So how's it going to redistribute or reparameterize?
What do you mean by reparameterize?
So what it's saying is, because you have a normal distribution, which is parameterized. The M is equal to this normal thing with U sigma. Yeah. So you can't differentiate samples with respect to this.
Yeah, that's what.
So what they're saying is, instead, you could add this, make something else called M bar, and make it sample as like approximately equal to standard normal with no parameters. They're saying in some fashion you're able to differentiate samples. This thing. But then if you do that, well, if you can compute a derivative of a sample with respect to, okay, so this is actually constant. So there's nothing to say about that. You wouldn't differentiate here. But what you are doing is treating this thing as being constant, like the distribution itself. And then you're saying, okay, well, when I sample this, I can just like do M is equal to, in some sense, equal to M bar plus mu times sigma. And then you should be able to differentiate with respect to the parameters. Be right this way. in some sense, because you're actually going to still get samples out.
Yeah, I mean, that makes sense.
But the samples should be stubbed in here. Oh yeah, it kind of does. Because you just write out your sample, whatever it is. X sample R. Differentiate this. No, it's not clear what this is. You're trying to get a number. Oh. Because this is going to be a number for each one of your actions. So they have the same dimension. The covariances are a little weird to me still, but I think they just treat all the non-variances as zero. They're saying in the definition back here.
You're saying that like is inherent in the R sample function?
Yeah, you don't have to do that manually. It's all in there. You just use the torch dot distributions, and then it'll come from here. Somebody should really write a clearer article about this stuff. I'm not going to do it because I feel like I still don't. I feel like I still would make a mistake and somebody yell at me. Or maybe I don't understand it all the way exactly. It feels right now like that is roughly what's going on. You just take your sample and you stub it in for the random variable, assuming it's not parameterized. Because, yeah, okay. Because imagine you just like literally you just sample this with the parameters. Well, then you get like X, some sample according to him. Well, how do you differentiate X with respect to the signal? Like, there's nothing really meaningful to say about it. So it's like a fake derivative, sort of. And it's technically you could do the same thing because you are actually just saying this is whatever this would be shifted by you and scaled by signal. And you can incorporate that into the thing, and it makes sense because like technically you would have still got the same sample, the same probability of getting it.
That's definitely a trick.
Yeah. Like it just feels wrong somehow, but like I can't pinpoint anything wrong with it. Probably still works. Just fine with it. But it's much simpler than the basic signal that's spinning up down. That's cool. This is way easier of an idea than I thought it was. But I still don't know what the partition function is, but you don't actually have to use that in the computer because it gets treated as a constant. So that's clear now. I don't think there's really anything else. Like, once we kind of know what's going on here, because these are normal distributions, so obviously you can R sample. Yeah.
Yeah.
Chain rule through, because your mu's and signals are the outputs, so you're just going to chain rule those through the parameters for the neural network. And you get your gradients. You have a particular sample, and it doesn't matter because
I think that Q, the S in the Q needs to have a dash over it.
these.
No. So in the minimization of the Q network, in the arguments, yeah, I think it's next to it. Instead of
Oh yeah, apostrophe. I think it didn't say it was. Let me make sure.
Really?
It's for the old ones, yep. So yeah, just to make sure I understand. What is happening is the actual outputs, policy network, are means, sigmas, and you're going to sample that. And then you're going to have, for each of your outputs, you're going to have like a particular component of the action vector, like AJ, theta, S, will be a number. And then you'll have like this, mu I, sorry, sigma I, and plus mu I. And so this just gets treated as a constant, J, sorry. This gets treated as a constant. And so when you do the differentiation, this just kind of like acts like a scalar for the sigmas. But it doesn't do anything for the mu's. Oh, you like caching the results from the neural network. And then once you sample it, you stick that in there. So these actually are all coming from the neural network.
Yeah. Trying to.
When you do the chain rule. Because these, you could write sub thetas, because they're actually doing neural network. So it's like, this is not exactly right. This should be normalized. And then use product rule. Yeah. So this never gets differentiated. And in fact, you can even rewrite it slightly, so it's like I'm going to try a bar. And so this is equal to, that's this guy, but then you want to put it in standard normal, so you do this. And then when you differentiate, you pretend this is a constant. So you differentiate with respect to sigma. So this is going to be properly the way to write this is like this. So differentiate with respect to sigma. That's going to give you A theta JS minus mu theta J over sigma theta J, and then times the derivative operator with respect to this. But then you do chain rule. So chain rule, and you differentiate this with respect to theta. Sigma And that's just straight up going from the neural network background. And then the other part is I'm missing the other part, which was this. And then you have to differentiate with respect to view. And you get just sigma coefficient. And you have your gradient with respect to view. And this is really what your sample was that you used. You're just normalizing it. It's never computed standard deviation. This actually isn't so bad.
Yeah.
Okay. I think now everything's fairly clear. And it'll just change if you don't use normals. If you use like a gamma distribution or something, you just get a different formula. But our sample kills any need for any of this. Okay. And the update step was this guy, and you just are doing more chain rules. This time through your Q network, you're saving this, differentiating the Q network with fixed action, and then multiplying with the gradient of the action with respect to the policy weights, and then the log distribution, or the log is simple. Okay. Not bad.
Yeah, I was thinking before about just the target update.
Yeah.
Pointing out this target is Y output, which affects the base function.
Which
Making that was a little wonky for me.
this part?
No, this Y output.
Yeah.
I mean, I got it down, but I just had to store some like extra variables, and then like on the update step, I had to like recompute this target from the batch. So, yeah.
Yeah, you actually. It's a little funny because this guy can change. So you can't just cache. You would think, looking at this, you already saved your batch. Why don't you just save your Q value? But,
Well, I mean, that's what I did do.
so you can't do that because this can update.
But, not before batch though.
What?
You're saying it can update like this is still summing up during some batch samples, so it shouldn't still be deterministic during that batch.
So you only end up with one replay buffer ever, and you never reset. So you can, you'll get to your update stuff, and then you'll do a few of these.
I just think we're using it, so
Yeah,
it has actually on a different.
Right. And because you're still going to use this state and this action from this old batch that happened 10 years ago, you're supposed to be using the current ways. So you can't cache your Q values. With this, what was tough was it like storing like the state after or something?
No. I mean, the state after is given to you. Yeah. So I just had to recompute the target value. I guess that might just be inherent through all of them. Yeah, I'd originally cache the queues, but yeah, you're right. I was just thinking about one batch.
I think, for one batch it worked fine. Exactly at 2 is where it starts to break down. You update your these guys. Literally every time corresponds to this. Yeah. Every batch you one update. Okay. Programming done. Zoom this in. I think I've forgotten Python. Give it a couple days. Okay. So I want stable baselines. Let's grab this code. Where do I control the size of this thing? NLP policy. Was I using my sizes earlier? So policy edit sizes. Keyword orders. Not there. sense. What's the log interval? Okay, it's just for logging. And I do want to save the model. To save this at os.app.join. Where is it failing? Model's not defined. Assertion error. Discrete for was provided. So you can only use box for your actions for SAC. You can't use discrete. Let's fix that. at all. This room is 329, right?
Yeah.
Okay. Miriam asked like an hour ago if it was 329. I just said yeah. No.
Oh, shit.
Like it literally said in 5 messages that it was. Okay. Do they have it implemented? They do. It's just in a slightly different library. And it was added. SAC. And it doesn't work.
This doesn't.
Yeah, it doesn't. So there's no existing implementation of discrete action space soft Actor-Critic. But we don't really have a discrete action space in our rocket, so it's okay. It's kind of a problem if we look at mixed, discrete, and continuous action space.
Well, there might be.
Probably is, right?
Yeah. You have to like choose a point to activate your thrusters. Because you go up, you kill the engine, and then you have to activate it, which is discrete. I think that would be it.
You could do clipping where you just make it like a negative number.
Yeah.
It doesn't turn it on. But then any jump at all to positive numbers is going to just fuck you up. They also have DQN policies that are similar to soft Actor-Critic in design, but or in spirit, but they are good at doing discrete action spaces. Let's see this one. That's some nonsense. I've seen people use GDPG.
Did you get discrete or?
Well, for Lunar Lander, you do.
I think they have a continuous
Let's see. Okay, you're right. So you just put a flag, continuous true. It's no better. Almost landed. This definitely feels a lot different than PPO did. Like it wavers and it tries to have less precise movement. Come on, just fly to the right. It's not loading it. Shit. Oops. So, I get training. Set the environment. Let's try increasing this. And 2 cards. Afterward. Better. Worse. It feels heavier to train this than it did to train PPO a little bit. But it's working, so not too bad. It may have something to do with the continuous action space, it's just going to take a while to start. It's higher dimensional, sort of. I guess the discrete action space is really zero dimensional. Okay, now it's working. Good stuff. So, one thing I just realized is you're updating after so many time steps. In PPO, you did a whole episode when you would update, so like this is much nicer. Because if you do really bad, the episodes are going to be really long and you're not going to have much to learn from. So you're just wasting a lot of time before you do your updates. In PPO. Now it's going real fast and steadily improving. It's actually 2 or 3 times faster than APO was. That video footage y'all got from the last weekend was pretty cool.
The falling one.
Well, sure. Who was it? I guess Kubra's was the cleanest.
Yeah, mine was. I got fucked with. Well,
Was yours the one that just like fell?
no, that was Providence.
Okay.
Yeah.
Chisholm didn't get to launch, did he?
He did. Yeah.
Okay.
I keep getting like I forgot about this. But last time I tried it, I got a dependency problem with his bots too easy. I'm getting like the same stuff. What can I do? I tried this one. I tried this other age. I haven't seen an issue with that.
Try this. Well, no, you can't do that. It's Windows. How do you?
Yeah, I could do sudo.
But you don't have the apt. That's a Debian only. So look up this website, I guess. swig.org/download.html. I guess that's the dependency. Well, it's not really wanting to take me there, so maybe it doesn't exist. Okay, let's see what we got. What the hell? For your flight video, the video starts with a 3, and then this ends up like halfway through before the video ends.
Yeah, we're gonna figure that out. Like the next click out.
It was the cleanest of the 3, though. It looked like.
Yeah, I mean, I don't know if you saw like the other perspective, but that was pretty straight.
Yeah. Kiara did the photography.
Yeah.
Who is that? I haven't met her.
Yeah, I mean, I hadn't met her beforehand, but
Is she like a photography student or something?
no, I think she's doing like, well, she's at Dunwoody.
Okay.
I think she's doing either civil engineering or chemical engineering.
Is that her own camera she brought?
It was just on her phone.
Oh, sure. It was like some DSLR / video camera thing. Come on, 200.
you know like anything about like multi-agent reinforcement learning?
I've seen things people have done. Like what do you wonder?
I mean, I was just like trying to look into it a little bit more.
I like the stuff people do with LLMs, with the little like, towns, and they have like a business or something that's listening there. That stuff's kind of cool. I want to do some like GRPO reinforcement learning type stuff on LLMs eventually.
Yeah.
I won't get time probably this semester. If I go to a place that has resources for training stuff. Cool to do that.
Are you gonna have any like LSTM lectures or?
We can do it for recurrent knowledge. I know how the transformer stuff works now. There is another thing called RWKB, which is it's like transformers in that it has like an attention kind of based mechanism, but it's a recurrent call that works and the context length is infinite, and it's really cheap. And there's no KB caching. So people have found that at least up to like 7 million parameter models, they actually outperform all of the existing LLMs. But this is like a community project, so there's no company behind it or anything. But why are you like interested in learning about LLM type stuff?
Well, yeah. I mean, I wanted to. It seems like transformer architecture is getting robotics pretty hard. So.
I mean, I could just show you how it works.
Yeah. I was just looking at some videos, so like, I understand like some of like the higher level concepts.
Yeah. Well, the computation is really easy. Like, you just actually have to do it to see what it is, because like the explanations don't stick in your head really easily. You want to do that now?
Sure.
I'll let this train for a little bit. It's getting worse, actually.
Yeah. Are you planning on still? It's not diluting the model, but locking it down to a smaller version.
Yeah. So we'll distill.
Yeah.
But this one's regressing a lot. It got up to like 190, and now it's 120 every episode. Weird. Maybe I need to do annealing of the entropy parameter. I don't know. Maybe the neural net isn't big enough. We start over twice as big. Create from scratch. Start that, and then we'll look at transformers. Where did I do it? Here. Oops. And actually, the people at the math department implementing GPT-2. That's not good at all. This is the whole thing. There's nothing about what's in this picture. So you don't take this whole thing for LLMs, you just take the right hand side, and it's kind of set up like an auto encoder. So you're able to put in something straight with words, and then it should come up with some kind of like compressed kernel, like embedding of a kernel for that, and then you can feed it to the decoder. This whole left side is the encoder, this is the decoder, so you really just look at this. And that's what is used for like GPT models. So you have to have a tokenization scheme. Usually what people do is show what that looks like. You've probably seen that. But this is a good out because you can actually check what the tokenization scheme is. So clearly not, let's just do this. So this looks like just words, yeah. But the is not going to be the same as the with the lowercase. So 30, 86, and 976. If I change this, we get 976 both times. So it is case sensitive. So anything you want to represent, you gotta have a separate token for. Case sensitivity needs that. But if you could even do this without representing the spaces, so you can actually throw them away if you wanted to, and then you can just have every possible word. So what you do is you say, okay, let's take a sequence of words. So we put around a box, and we're going to try to predict the next word. So this is the input, this is the context. Now you got to tokenize that. So you decide on some token scheme. You can do byte level, so per character, or you can do word, anything. You byte chunk, like here. I think this is the GPT tokenizer. That's how that would work. But you might also just tokenize this, like this is a token, this is a token, this is a token, this is a token. And then you want to output Jones as the next token, much like. So how do you actually do that? Well, each of the tokens gets encoded as what we call a one-hot encoding vector. So V gets encoded as, well, that is 976. The index of the token. You have to have a number for every possible token that you want to represent. So you'll come up with a vector that's zeros. Really, in this model, it's a row vector. So you'll have 0, and then you'll have 971, or 975 zeros, and then 1, 976, and then 977 is going to be 0, and then it's going to go up to what we call BT, the dimension of the token space. This is X. call x1 and 1. And then similarly, quick. This is going to get encoded as 4853. And that'll be another row vector. And this will also be outside of dt. So this is in RDT. The main thing to understand is like the sizes of the vector spaces for all this stuff. So the way you take this whole sequence and you make it into something the computer can pick is you come up with this matrix X. And this is a context length of 4 tokens. So length is like S equals 4. S is going to be the size of it. So there's going to be a separate row for each token. There's going to be 4 tokens. That's going to be a S by ET matrix. Many columns as there are positive tokens, and as many rows as there are tokens in the T. And they can repeat, so you can have 2 of the same row if you want. D and D. Okay, so in the picture, so far we just have this. That's X. Now, you don't actually represent that in memory. It's the RDT part, or the DT column with the super huge billions. So you don't actually do that. There's a trick that you'll see in a second where you won't have to. Just because you're only doing matrix multiplications all the way through here. So now we need something called the embedding, the word embedding. So we're going to come up with a matrix, WE. And this is going to be, we're going to end up multiplying. So let's say Y equals, I'm going to actually change this X to Y. So X now, Y is the token sequence rows, and then X is going to be a matrix gotten by multiplying Y times WE. So what I need to do is I need to figure out some embedding space dimension. We're going to call that D. Let's see, DE. So this is going to be a matrix now, and it's going to have a row for every token in the sequence. So S. S by ET. This would be S by no longer ET, but DE now. Whatever the dimension of the embedding space is. That's usually going to be less than ET, probably like 26 or something. Not huge, usually power 2. And this is just going to be a matrix that we learned. So we're going to be backpropping with data entries this matrix. So this has to be, because we're going to multiply it with Y, the left side has to match this dimension. And we're going to end up with this after the multiplication, so we can find E. That's the dimension of that. And I know that I don't need to actually store everything in the Y matrix, but we will actually have to store as many columns in this embedding matrix as there are possible tokens, so it is expensive to store this. That's okay. I think, yeah, that's the only place that the DT actually shows up on the computer. You could probably also use like low rank decompositions for that if you want to. So what this does is it takes these vectors here. So D is going to be like a vector in some direction in length 1, and then quick is going to be a vector in another direction orthogonal to it with length 1. And then brown is going to be another one in some orthogonal direction. And they have nothing to do with each other because they're not pointing at all in the same kind of subspace. When you multiply them by the embedding matrix, it's going to send them to somewhere where they kind of have the same, they project on each other and non-zero projections. And the amount that the projections are. So like you can do dot products. So like if you take x1, let's say y1, y2. So y1 is the one I'm embedding for D, y2 is the one I'm embedding for quick. Those probably don't have anything to do with each other, so y1 dot y2, well, that doesn't make any sense because it's 1 pi, so there is 0. But if I do y1 multiplied on the right by WB dot y2 multiplied on the right by WB, this will be close to 0, but not exactly. There's some overlap in like agreement in the meeting. But if I change the order they appear in the sequence, it doesn't change anything. I haven't coded anything about that yet. But that gets us to here. So this is going to be, this is y, this is x equals YWE. Just encoding common meanings. The purposes of, and somebody's like watching a video of this or something. Like cat and dog. Is that what Y1? Dog or Y2? Then they probably both agree in like something like a pet axis. So you can imagine the embedding space, it's like 3D or something, or 2D. You might have like something like this being the direction that corresponds in general to house pets. Or things like this might be the positive direction, this is the negative direction or something. You can just assign that kind of meaning to it. Maybe cat and dog are like this. So this would be like Y1 WE. This would be Y2 WE. So cat's embedding, dog's embedding, and then you might have like spider or something, or monkey, and it wouldn't be a good house pet, so it would have like opposite meaning, but it would lie in the same subspace, or at least be close to it, project onto it. And projections are just this, just 90-degree projections. You just take the length of that and scale it other one. So if this is more than 1, it's going to increase the length of this vector, this project vector, and so on. Usual dot product stuff. That's what the embedding does. This whole thing about output, don't even think about that. This is really an input in our context. Okay, so that gets us there. We have X, which is an S by DE matrix now, and it has a row for every token in a sequence, and columns are just the components of the embedding space. So, the positional encoding now, you come up with some matrix P. So, this is not going to be learned. W is learned. Anything I write W is going to be learned, and everything else is not learned. You just do those through backprop and gradient descent. P is going to be a matrix, and it's going to be an infinite row matrix by DE columns. So it'll have a column for every dimension of the embedding space, and it will have no limit to the rows. So, does that bother you?
Yeah.
Okay. So what it is it's pre-decided. When you make an LLM, you figure out what this matrix P is going to be. You've already decided for your LLM what the embedding space dimension is, so that's a fixed constant. And this infinity is just the following. We're going to write P as a matrix, and I'm going to write the bottom of it because it keeps going forever. It's going to be one row here, P1 and P2, another row, P3, and so on. And it just keeps going. And I'm never actually going to have this in practice computed out all the way, of course. But in practice, what I'm going to do is I'm going to truncate up to PS. So if I have a token sequence of length S, or
4 or something, I just go up to 4 rows. But this actually does go on forever. It's just that I only look at parts of it depending on how long the context is. So really, this could be like context max or something instead of infinity. But you just come up with math formulas for saying what row am I on? Well, this is what P1 should look like, or P30 or whatever. Really, it's an infinity usually. And in the paper for transformers, they do this thing with sines and cosines with different frequencies and amplitudes. And those end up giving the entrance for each of the P rows. Actually, show it. Here. So for all of the even index rows, and they do it backwards. So they say position. I'm not right. This is the row. This is the column. So for each of the even index columns, you'll take this formula and use the sum. And for each of the odd index columns, even columns, odd columns, you'll use cosine. And it's the same thing put into each of them. I think the model is the embedding space dimension. DE in that case. And position is just what row you're on. So that's like P1, 1 would be position. And then you just put I as the column. Or 2I as the column, maybe -1.
But it really does not matter what you put. There are some choices of functions that will work better than others, but that is for the mathematicians to figure out.
And in principle, it doesn't matter what they are. It's just that they all need to be different. You can't have the same one twice. Now, what you do next is you, what do we want to call this? I guess Z. So we're going to make a new matrix Z, and this is going to be defined to be X plus P, truncated up to the S row. So this is going to be of the same dimension as X was. Same size. So S I P E. S many rows, P many columns. And so what this is going to do is it takes all your embedded vectors, embedding space, and think if we had like cat and dog. Well, if I had a token sequence, which is just like the cat or the dog, well, cat appears in the second entry, dog appears in the fifth entry, and so you have like P1 or P2, P5, say. Those get added to these, and so like P2 might be something like this, P5 might be something like this, and so dog would get moved to here. That would be the positionally encoded dog, and cat might be here once it's positionally encoded. And so what's going to happen is when you do gradient descent on your embedding matrix, it's actually going to learn to embed the vectors in such a way so that, firstly, their meanings are correlated based on projections, but also you're avoiding having the meanings messed up by the common appearances of the words in the sentence, like where they appear. So it's going to kind of learn to exploit the positional encoding matrix. So this call comes from free from the gradient descent. That gets you here. So this is going to be Z. And again, this is S by DE. This is S by DT. And this is going to be YWE plus P, just expanding X. And that's going to be S by DE as well. Okay. So now you've got your, and this happens for every Okay, it's not just for related weights, so every one of these is going to get perturbed a little bit by the positional code in the embedding space. So now, you have the actual attention mechanism. The way to read the diagram is just look at, like, this plus means absolutely nothing. I mean, this is P, and then it's adding it to whatever that is, which is Y, or X. And so then you get X plus P. And it's going to send it up through here, and it's going to branch. So X plus P, or Z, is going to go one way up here, and it's also going to get processed through here. And you're going to take the results of whatever the tension spits out, and then add it to the original Z. So basically, you're taking the tension of Z plus Z, and then you'll do this add and norm operation.
So this is staying the same as by the
It does. Yeah.
like all throughout? Or
Let's see.
is after before the people?
It will up to linear.
Yeah.
And then linear is going to spit out budgets, which are numbers that you can softmax to get probabilities.
Yeah.
So the linear is going to spit out something, a vector of length dt, the size of the token space. And linear is just like feed-forward network, very simple. But this is like a residual connection. So it's trying to say, okay, attention might learn some really weird stuff. You kind of just want to keep some of the meaning of the original words intrinsically. You could take that out and just have really just the attention and just go straight to the linear, and then you'd be fine. But you don't have to. It works better to do this whole thing. So this is just to improve performance. So really, all that's left to really understand is this thing. I mean, this is simple. You know how it works. Linear is the same thing. It's just one layer feed forward. And there's no ReLU or like simulated functions or anything. But feed forward does have the ReLU. And so, yeah, this is like me. So there are a bunch of details in this that are not pure attention. We don't need multi-head. So that's going to make these two go away. And you'll just have this one. So you're going to take Z, and you're going to plug it straight into the attention mechanism. Yeah. And you do need masking. But let's see that. So let's just look at single-headed. Okay. So the attention mechanism goes like this. So it's a function. It eats Z. And it's going to spit out a matrix. It should, because you're going to be adding it to the residual connection with Z, it should have the outcome from the attention should have the same shape as a matrix as Z did. So whatever the shape of Z was, which was S by DE, so too should the outcome of attention have that shape. So it goes like this. I'm going to define three new matrices. They're going to be W, Q, W, K, W, B. And we're not going to worry just yet about what the shapes are. We'll figure it out. But Q, K, and B are going to be defined from them. And they're going to be Z times WQ, Z times WK, and Z times WB. And again, these are large matrices because they're W's. Now, let's see. This will have shape S by, I think, DE. That's not correct. It's going to have a new thing here. It's all in the same shape. But the right sides will be PE clearly because I'm taking that's not left sides are like S, because Z and shape S by D. We're multiplying it with W. On the right side, you're going to have something else called, in single head attention, it's going to be just DE, but here it's going to be B for multi-head attention in general. But for single, we'll just use DE. If you have single head attention, it's definitely going to be that way. So the shape of these, because we're going to multiply them with Z, which had dimension S by DE, these need to be DE by DE. So they're all square matrices. In multi-head attention, they will not be square anymore. They will be rows stay the same as less columns. They'll be tall matrices in multi-head attention. So you just learn these matrices, you can backdrop and gradient descent, and you just multiply them with Z. Now, the attention mechanism is a function, and people like to write it this way, even though it's really just a function of Z. They like to write QKB, which is these three matrices, and it's defined like this. So it's a softmax. Then you do Q, K transpose, divided by the square root of DE plus M, which is a matrix I haven't defined yet, times B. Okay. So this is hard to understand. It's not very clear what's going on. So I'm going to come up with this basic thing called full attention. And it is not going to use Q and K. It's going to use something else called D. And it's going to look a little bit different. And out of D, it's actually going to use WK or WB. And it will be Z, Z transpose over square root of DE plus M times Z WB. All right. So what this is doing is M is a matrix. Actually, let's just look at this part. So Z, D, Z transpose. So Z is in the embedding space. It's a bunch of vectors, the rows of vectors in the embedding space. And so Z is like Z1, it's the embedded and positionally encoded version of D, Z2, Z3, and Z4 for Fox. Okay. Now, you can imagine what they look like in 2D, for example, if the embedding range is 2. D might be here, quick might be here, brown here, Fox maybe here. And so if I take D, D is a square matrix of size DE by DE. It is going to take a vector in here and it's going to act on a single vector. So if I did Zi, some particular word with that, there's D, Zi transpose. That is going to take this and it's going to like convert it to a number. It's going to act like taking Zi times Zi transpose, which is a number, and it's the length squared, but it's going to weight certain directions more than others. So like it might act like a radius for this would be like this. That's all vectors in the same radius as that one. but B can pick out an ellipse shape, and it will make like this kind of thing. So this would have the same Z, D, Z transpose as this vector would. So it can just pick arbitrary stuff. And you're going to actually learn B in this case, if we use full attention. Now the thing is, we're not just doing it on individuals, we're actually doing it on all of Z. So what it's going to do is it's going to say, well, you can imagine doing Zi times Zj transpose, which would be two words, and you're projecting them on each other. And they're positionally encoded in one. But then you're also going to apply D, so you're going to weight particular projection directions. So this is going to, it's going to capture the interrelations between words. And it's going to be pairwise for every pair of words. And so the outcome in Z, D, Z transpose is going to be the matrix size S by S. S by S matrix. And this one's going to be Z1, D, Z1 transpose. This one will be Z1, D, Z2 transpose. Z1, D, sorry, Z2, D, Z1 transpose, and so on. So just grab the interrelations between words. And basically it's encoding some kind of latent embedding space, because they're all numbers. It's encoding some kind of latent embedding space correlation between each of the words. So like Z1, B, Z2 transpose is encoding how much you know about, let's see, I'm trying to think of the direction. So this one is, if you wanted to come up with a meaning for Z1, given the knowledge of Z2, this tells you how much information, according to like B's definition of the embedding space, is encoded in Z2 about Z1. Okay. So it just captures this correlation quantities, so to speak. And it turns out actually that this is going to be enough once we do this WE stuff to get everything we need for like figuring out the meaning behind sentences. But you don't have information, so like if I have when I read Brown, I don't know if Fox is coming from the sentence. So I shouldn't be using the information about Fox.
That's why you mask.
Yes. So the mask is defined like this. It's a strictly upper triangular matrix. And it has 0 on the diagonal and 0 down here on the bottom part. And then on the top, it's got negative infinities. So that's it. And this Z, D, Z transpose is just capturing the correlations. So the way they want you to think of this up here is this actually, I'll show in a second, is a low rank factorization of this. And the reason I write Q and K is because Q is the word that you are looking with. So like if you're looking with Brown, you want to look back and see how much of the previous sentence encodes. So what you're trying to do is figure out the next token. So you're saying, okay, I need to look in the sentence, see what meaning is in the words in the sentence, and then I need to look at sentence level information based on that word that I'm looking at right now. So the word I'm looking at is a query, and the keys in our matching list for information are the previous words in the sentence. And then I want to convert that into like a hash lookup almost for a table in values, where I say, okay, if I'm looking with a particular query of Brown, maybe I'm looking for objects or modifiers earlier in the sentence that tell me about brown things. And then using that sentence level correlation, I should be able to get better information about this. But it depends on this brownness idea. So we want to actually like have something, because this is only telling us relation numbers, like intensities of correlation between things. So I need to have some way to look up what those intensities correspond to with respect to the word brown. Here in just a second. And not only brown, but like also the word that they correlate to. So if D is a strong modifier for brown, the number up there in Z transpose is going to be far away from 0. And so I should be able to use the knowledge that this is D, this is brown, and they're strongly related to come up with some part of the embedding space that corresponds to brown being modified by D. So that's what values are going to do. So it's like a latent correlated key value lookup. Okay. So that's what I call them this. And all you're doing then is you're just saying, okay, take this matrix, convert these guys into probabilities, and they're going to be convex combinations, like the coefficients of convex combination, basically weights. Or the you're going to take Z, so that's everything later in the sentence, or even previous, and it's going to extract the mean from brown and B, and it's going to say, hey, those are related. Map via this learned embedded matrix, this correlation that we've gotten from D and brown onto things that are D and brown in the embedding space. So like a car might be D and brown. Like you might be talking about a specific car and be a brown car. And so like this should probably send such correlations to places in the embedding space that have those properties. What's weird is that like there's not really a more formal way to put this. Like people who invented this had this kind of like soft explanation for them, developed it. So it's like
Yeah, I heard it. I tried reading this a little bit, but I heard it was not great, I guess.
Yeah, it's very like intuitive. There's not like you can't say this part of the algorithm does this. You have to say, okay, I get that intuitive. I get why this should make it work. That's all you can really get. The gradient descent's doing all the heavy lifting. So the correlation or the correspondence between attention and full attention would be, well, just this thing. So what I'm claiming is I should be able to say, okay, it's possible that these are equivalent things. So I'm going to ask, is this possible? Does the query E thing correspond to this quadratic form on Z? Well, you can just expand this. This is ZWQ. This is ZWK transpose. Well, when you transpose the product of something, it's going to flip the order. And you transpose the factors. And then by associativity, you can group these. And then the claim is, well, if you want this to be equal to this, it is possible. It's just that this thing has to be D. The DPA matrix of size S by S, this has to be one of the factors in the two matrices. And because these two matrices have size DE by DE, it is possible that the context length is longer, which is S, is longer than the embedding space dimension, DE. And if that's the case, then these matrices have rank DE at most, and D has rank S at most. And so it's possible that the rank of D is too large for this factorization to actually work. So this is some kind of low rank factorization. And that is just used to make the the computational expense go from S squared to S, or excuse me, DE squared to DE. So it cuts you from a quadratic complexity to linear. And it makes you train faster, it makes it cheaper to run inference, all this. So this is fine. And then you can throw away full attention and kind of it makes more sense. You're just thinking about making these ellipses in the embedding space where you're deforming the projections by. And then that's the whole mechanism. And then you get out at the end, the softmaxes, because the softmax is going to take negative infinity and add it to 0. Because it's the least possible thing, and so making the probability is equal to 0. So this is a bunch of things between 0 and 1, and multiplying it with b. And remember, m had dimension whatever q times k transpose was. So q is dimension s by dE. So q times k transpose has to have dimension s by s. So too does m. So this whole thing is dimension s by s, or size s by s. B is size s by dE. So this whole thing has dimension or size s by dE. And that's what comes out the top. Here. So this is tension QKB. So that's almost everything. Like, there's nothing missing here that you wouldn't be able to write on your own on Python. But the multi-head part is a little funny. So when you took this whole thing and you plugged it into the attention mechanism, you had to form these three matrices and multiply Z. Well, with multi-head, you usually want to take 8 for the number of heads. I think that's what they use for GPT-2. And what you're going to do is you're going to say, how many heads do you want? So we'll say H equals 8. The thing coming in is Z. And Z has dimension S by dE. So it's all the tokens embedded. And so you are going to form, this would be if H is 3. 1, 2, 3. So you're going to form 3 matrices. So they're going to be W head 1 through W head 8 through W head H. And this time you're going to form, you're going to come up with something called dk, which is equal to dE over H. Okay. D. We just call this dH. So the dimensions of the embedded space in a single head. And you're going to project Z. You don't have to do this. This is kind of unnecessary. You can just make these guys be smaller. So the right sides will go to DH instead of DE. And then when you do your attention mechanism, you won't take the square root of DE anymore, you'll take DH and all this. And what this is going to do is it's going to take your vectors in your embedding space, say dimension 2, and get 2 heads. You might have a vector like this, might have a vector like this, and it's going to pick projections of the whole embedding space, and each head is going to get a projected down version. So, like the first head, you have 2 heads, because they need to be this is two dimensions, you got two heads, so it's going to project onto one dimension each. Well, the vectors might end up being like, this is the axis of projection for the first one. So you end up getting something like this. Your vector, isn't it? The other axis of projection might be something like this. So this ends up being here, here.
So do these heads like then correlate to like specializations within some?
Yeah, so they have done studies where they'll look at what the latent meaning is, and they'll try to probe and see what gets high activations in the query key matrix. And they'll find like some of them are used for like spatial relations, or some will be used for like grammatical understanding or something. So the heads do tend to specialize. But yeah, you literally just equipartition your inputs into different dimensions. But it isn't the case that like the axes of projection will always be different. They can be the same. You just won't get any efficiencies with having that. If you have that, you can literally delete the attention head. It would work the same. Be faster. You then just add norm outputs. I forget how you add norm. I think you. I think it is a layer norm if you do. Because you're taking two S by DE things, two S by DE matrices, which is Z and the tension. I'll just call it A. And you add them, and then you got to normalize them now. You got these two matrices, and they're embeddings of your token sequence. And you
Yeah, it's typical layer norm.
So I think you literally just take whatever this matrix comes out being and you normalize it. So that it has like unit for radius norm, which is like the sum of all the squares of the entries.
You just want it to be 1 for that sum. But that's it. There's no magic. It's just these matrices with that problem.
And so what came after transform is now people got this word for LLMs. Somebody really early on said, okay, well, we had this problem because every time I want to get the next token, I got to recompute everything from scratch. It's very expensive. So where is the expense coming in? Well, it's coming in when we compute the attention, mostly. I mean, there's other expenses that are big, but the ones that we can actually optimize is the attention. Because what's happening is you have these S many rows in these matrices for Z, and then Q, K, and B. And so you can say, well, where are those coming from? Well, Z, think of what Z is. It's equal to Y, WE plus P. Y is mostly not changing every time. And so correspondingly, WE never changes until you do an update. This whole thing is only changing in the first, it's deleting the first, it is adding one more row every time you generate a new token. And so you've already computed everything in it. And so this is also not changing. You're just adding another row in. So the whole thing is staying the same. You're just adding an extra row. So why don't you just save it? People say, okay, let's save it. And then correspondingly, these don't update, except in the last row. They're S and E. And these don't change until you do background train some more. So just save everything, QKV. And this gives you what's called KV caching. If you look it up online, it's like this. KV cache. Can't think of why it isn't QKV cache. Doesn't make sense to me. But this is really slow, and it's like several hundred gigabytes of memory you gotta keep. So DeepSeek came up. People tried things to improve this by like, as you can imagine, you have in your attention mechanism, you got Z coming in. It's getting multiplied with these matrices. So Q, you get all your heads firstly, so it's going to split into your heads. You'll have Q's getting computed, K's getting computed, multiplied with it, computing this thing, multiplying with V. This does change radically every time, so you can't just. Can you cache everything except the last row and column? This is going to be the same there. This is the new one. This is the new one for K. So you end up getting this being the same. As long as you're not on the last part, you're the same. That's all the same. The QK transpose. And B stays mostly the same. How do you draw this diagram? For V2. So this is the old way of doing MHA. And Meta, with their llama models, I think they developed GQA, which is group query. So each head still gets its own query matrix. And you cache that. And they have you can see for two heads, they'll have one key, one value matrix. So they just share all across. So it's like I was saying, some attention heads might be the same behavior. Well, you can just group the keys and values for a couple of them. And it'll improve the performance and not hurt, or it'll improve the speed and not hurt the task performance as much. And I think Meta was the one that tried this first. So they just did literally one key value matrix. the whole thing for each attention block. And it does improve the speed a lot, but like I think it's a reduction to like just a couple of gigabytes of memory slow for the KB cache, but the performance drops so bad that like it's like a 40% reduction on the wall benchmarks. And it takes longer to train. You don't actually gain any speed improvement in training from KB caching because you're updating your. I mean, you can if you like run a few inference steps, but if you update it on every inference step, you wouldn't be able to cache anything. So you'll run the task a little while and generate a very long answer, and then you'll update steps. So it does save you some time on training, but it would be nice if you could update more frequently during the training, so you didn't have to keep a KB cache. But DeepSeek came up with this thing where instead of actually storing matrices, like the rows of matrices, they will come up with this projection to another embedding space for the KB cache, and then they'll load that back through like some kind of variational autoencoder, and they won't even use key and value attention anymore. So that gives them, I think, 57% improvement on flops, or 57 times improvement, so 5,700% improvement on flops, and storage space. I think it's 6 times for improvement on flops, so computational complexity, 57 times reduction in space complexity, and they only see like a 5% reduction in benchmarks usually. And then they can scale the model way up because they've got inference time compute now. It's way cheaper with this. So MLA is what everybody uses right now. But they have this nice paper that literally shows in like 5 formulas how to compute the thing. Really simple. And their papers are easier to read than the old stuff. Like when you get to actually implementing it, you can almost just read it right off the paper and just put it in the computer. So.
Yeah, I wish like more papers were like that.
Yeah. Something about having like mathematicians as your employees makes you write simpler papers. But there's also a video about this that it's actually easier to just read the paper, but the video has nice visualizations. And they have all these little tricks that let them make V2 better than the long models. It just sucks that nobody will publish their stuff except DeepSeek. Mm-hmm. Yeah, that's kind of the whole story, honestly.
Yeah, I think NVIDIA, they just did some collab with Disney, and it was someone else. I think it might have been DeepMind. I think it is DeepMind. They made their supposedly they made their transformer architecture open source. I don't know what to see how open source it is.
Is it for like robotics or something?
Yeah, like they made this like Disney robot or whatever.
Is it the little 2-leg thing from Star Wars?
Yeah.
I think the Gemma models are open source. I just put one out a couple days ago. But they're not as well documented. So yeah, the DeepSeek papers are like gold for everybody in the field. I don't like this paper. Like they don't even tell you how the masking works. Like if you haven't seen it before, you just don't know. Oh, and with multi-head, at the end, you get out. Yeah, you have all these attention layers. They're actually pre-computing QKB, doing that linear projection onto the smaller dimensional subspaces in the embedding space, and then they'll feed those into one attention head to get another behind it and then another behind it. So H in this case would be 3. And then you'll get out these S by DH matrices as a result of the attention instead of S by DE. So it's going to be S by DE divided by 3. So you take those and just take the columns and you lay them side by side and concatenate, and then you do it linear layer, and then get you multi-head. It's very simple. Yeah. And this introduces another matrix. You get these three, they learn, and just one. And that's it. The rest is just like how do you tokenize images, which I haven't read about. This is just for. So you have some kind of variational autoencoder linked to the convolutional neural network, and you feed in the kernels of the images that the convolutional autoencoder spits out into the attention mechanism. But yeah, you get logits out at the end, you softmax them, and you get a probability distribution for all the tokens that you want to output. And then you just sample that probability distribution and it should spit out Jones. And have you seen the temperature for the other ones? Like some of the old stuff and like temperature parameters you could tune?
Yeah, I mean, trying to remember. I know it was just correlated with like some variability and like how, like what you sample.
It is, yeah. So when you at the end you'll get the probability distribution, which is I'll just call it pi. Be a quick round box. And then you'll have like a vector probabilities, and maybe this one is like jumps, leaps, dies. And so this probably has like 0.8 or something. This might be like 0.1, 0.1. So what happens is if you have temperature equal to 1, you just sample this. So we'll call this 1. But if you have temperature 0, then you'll get a vector out that's 1, 0, 0. So it is like an R max. And then you sample that. And temperature is a scalar that, let's see, gets applied to the logits. So the way it works is, because this is going to be a softmax of some numbers. But if you do 0, it's going to do this. And you can't really do 0, you do some small epsilon, like 10 to the -6. But it's going to be 50
10 to the negative 6 times 50, negative 20, negative 20. So it makes these go all very close to 0. And the way softmax works, it's like, it's,
I know the shape of softmax.
I mean, it's going to make things that are, when everything's close to 0, the stuff that's the furthest away is going to be like super heavily weighted. So yeah, basically, if you make it close to 0 temperature, that's going to be lower entropy. If you increase the temperature, it just fuses the numbers so they're closer to each other. That's all it does. It's just a scale over from the softmax. I don't think there's anything else at all. There were a couple of guys on Twitter who made this thing called entropics. And they were computing the cross entropy of something, I don't know exactly what. And they were coming up with a sampling scheme that firstly plots the cross entropy in real time as you're generating tokens, so you can see like how sure the model is with the tokens it's outputting. And they were able to make it like keep thinking harder and harder until it was able to get low entropy. So they found that actually improved performance on math and coding tasks. People don't really play with it anymore. It's computed. It looks like the training is done, so this should perform well now.
Oh yeah. Super quick. Oh, that's horrible. Okay, so let me update that. And where is variant? Adaptive Dirichlet step. D-slider. Compute these from their log probs. So P is jnp.exp log P, so those are the probabilities. That's the entropy, int. It's the log probability plus. Rocket works.
Oh, nice.
Somewhat. Well, sometimes. There we go. It like drops harder than the discrete one did.
Yeah. I know that was like some proof that like the optimal like
Reward.
I guess but like action is that kind of like belly flop where you like activate it like just before.
Yeah. Yeah, because it wants to minimize the time it spends away from the goal position.
Yeah.
Presumably, if you added like wind dynamics or something, it would try to come in slower just because it's more likely to crash. Yeah. So this entropics thing is really simple. Maximize it.
P equals the probability distribution. PDT is the probability of the tokens. Log P equals ln of P for each of the probabilities. Entropy is negative sun I equals 1 to dt p I log p ln p I and bare entropy. Diff equals log p plus all rows and columns. Axis. That's P1 plus P2 plus N column PT dt plus N. Then where equals sum over all p's. That equals 1 dt p I plus times diff ln p I plus pi int. 2p pi LADI.
Read my information theory textbook. It's a little bit beyond me.